Okay, so I think it's maybe best if we start off by actually writing down what Bayes' theorem is, and then we can have a look at the derivation of it and how to actually get to it. So in its most basic form, I'm not going to use any kind of machine learning notation here, we're just going to do pure maths, and then we'll substitute in stuff that we might actually use within our machine learning concepts and implementations really. So it'll make more sense later on. Right, so this is our basic form of Bayes, and we're going to have a look at how to actually derive this, and then we'll have a look at what the elements actually mean. So right now it probably does not mean much if you haven't met it before. If you have, you might have a vague idea of what it actually is, but the kind of underlying power is what we're going to try to get at eventually. So I mean, we can arrive at this by using the properties of conditional probabilities. So we can go and say that the probability of A given B will be the probability of A intersect B over the probability of B. Now what does this part mean, this A intersect B? So if we quickly switch over to set notation a bit, and then we can have a look at a typical Venn diagram of, let's say, two groups of things, A and B. Of course, this box is the set of everything, but we won't get into much detail. So where is the intersect? Over here. So that's basically the area that we're examining in the numerator of this expression. So this is where both A and B exist together at the same time. Now moving back to our expression, we can also write down essentially the opposite. So we can go the probability of B given A is the probability, and this is the interesting part, it's the same. So it's A intersect B divided by the probability of A on this, in this case, however. But the top is the same. And so this is essentially where the derivation comes in. So as you can see, we have the same terms here and here. We can rearrange and equate a bit. So then we end up with this. And then hopefully from here you can see that after rearranging by pulling B down here, the probability of B occurring, pulling it down here, we get back to our original derivation. So I mean, this is a quick derivation of the Bayes theorem. So now, if we try to have a look at a more kind of machine learning-y way of approaching this problem, so of again looking at this top, this is actually Bayes theorem, and then just having a look at how we can actually use this within machine learning and how it might apply to our problems that we might encounter. So now let's have a look, and I'm going to rewrite it, but I'm going to put in some new notation. And then I'll just write it down quickly, and then we're going to go into considerably more detail about what these terms actually mean and what the symbols within them actually mean. Alright, so this is something that we'll probably encounter quite a lot as we move forward. But basically omega I, so that is class I. And a lot of the problems and kind of examples I will be using throughout, there will be two class problems. So we're going to be looking at I being either 1 or 2. We'll start, or you can say 0 or 1. It depends if you have a programming mindset or not. Anyway, it doesn't matter. So it's basically just an individual class that can iterate over each class. And then X is the feature that we have observed, so the measurement that we have made. So quite often this is our classification task. We have a feature, we have a measurement that we've made. Let's say we have a bunch of fish on a conveyor belt. We have two classes. It's either sea bass or trout, let's say. And then based on the measurement of their weight, so that's going to be our X, we're going to try and determine which class that specific fish that we are observing at that moment in time belongs to. Is it a sea bass or is it a trout? And now this is quite a difficult problem to solve. And that's why we have to use Bayes. Now, what are the components of Bayes? So we have this, essentially the flipped version of this. So that's quite interesting. So here we have, we're considering a specific class, let's say CBAS, and we are examining the probability that we are taking that specific measurement from that class. So if we have, for example, the CBAS class, what is the chance, what is the probability that if we make a measurement, it's going to be 10 kilos, let's say. Now, I have no idea if that's anything that a CBAS might weigh, but let's say it's that. So this is essentially when, for example, it can be a uniform distribution, the Gaussian distribution, any distribution you can imagine, or PDF. And we're going to have a look at the Gaussian a lot more because that does appear a lot in nature and then in the practical application as well. So we'll be looking at those throughout. So this is the probability of that class occurring. So as you can see, there is no X term in here. So this, if we take the most simple decision method, we could say that, okay, we have let's say a training sample, and let's say out of 100 fish that we have a look at, 60 of them are sea bass, and only 40 of them are trout. So without taking a measurement, if that's all the information that we have, we will make the least amount of error if we always classify as sea bass. So 6% of the time we'll get it right if we always say, no matter what the weight of the fish is, because we're not measuring it, as long as a fish comes in, we say it's sea bass. We don't even look at it. So that will result in the least amount of error. It will result in an error rate of 40%. However, if we did it the other way, and said every single fish was trout, we'd get it right 40% of the time, but get it wrong 60% of the time. And so that's why it's, if you have no measurements, then you can use this. But of course, this is an extremely primitive way of doing stuff. So now we have the probability of X occurring. Now this is always quite a tricky one to determine, and sometimes it can be an indefinite integral that can be extremely difficult to so sometimes this probability of, and this is the probability of X. So this can be quite difficult to find out in real life, as it's usually an unsightly integral and it may or may not have a closed form solution. So we usually try to get rid of this. And now to have a look at the technical names of all these, this is called the a posteriori probability. This is the class conditional density function. So as I said, quite often Gaussian. This is the a priori. And this on the bottom, the P of X, is what we refer to as the marginal probability. So now there is a way to get rid of this, because as I said, it's always, I mean, it's not always, it's usually quite difficult to figure out how to actually get an answer for it in real life. So if we have the equation for Bayes' theorem, as I've just written here, there's a neat little trick that we can do to get rid of this unsightly integral, this P of X, because we do want to try to get rid of it and try to solve our decision problem without having to actually calculate it, because it will get tricky in real life. So there's this neat little trick that we can do. And we can say the probability of not omega I given X equals the probability of X given not omega I divided by the probability of X. Now, I'll quickly just kind of allow us to wrap our heads around what this not omega I means. So perhaps it's easiest to demonstrate with an example. Again, if we continue our sea bass trout 2 class problem, it can be easy to see that if we have X, our measurement, let's say it's their weight, is 10 kilos. This top expression allows us to calculate the probability, given we've taken that measurement, that it belongs to, let's say, sea bass. Let's say class 1. Now this allows us to calculate the probability that given that same measurement of weight 10 kilos, what is the probability that it belongs to not sea bass? However, in our 2 class problem, that means what is the probability that that particular fish belongs to the trout class? Okay, so that's all this not omega I means. And in the same way, you can extend it to 3, 4, 5, as many classes as you want. And here's the trick that we're going to do. Knowing that, we'll add them up. And as you can see, when you add these two terms up, it will equal 1. And again, in our two-class problem, it's easy to see why. Probabilities have to add up to 1. We've taken our measurement. If it doesn't belong to the CBAS class, it must belong to the trap class. But the probability, the summed up probability of those two classes, must be 1. So now we can rewrite this expression as this. And then, of course, there is a common denominator. So we're going to just put them all into one line, and then we can divide by that common denominator. Now at this point you can see that we can simply move it up, simply rearrange the equation. And so let me just be cheeky and do this. So this is our expression that we have now gotten for P of x. So now, in this case, we can substitute this expression back into here. And then now, of course, we have quite a big denominator, so of course, divided like that. So as you can see, what this has allowed us to do is get rid of this so-called unsightly integral. I keep referring back to the unsightly integral, this P of x. It's allowed us to get rid of it, so we don't have to actually calculate it. And now we can replace it with this. And quite often this is a lot easier to calculate, so the fact that the probabilities generally add up to 1, if we know already the probability of one class occurring, or we either know it through experiments, or somehow we know it, maybe it's given in the question if this is for college or university, then it becomes quite easy to evaluate the rest of it. And so this is a neat little trick that you can often use in real life as well, but also, again, for problems. Thank you for listening, and yeah, I hope it's been useful somewhat.